Okay,
No,
so
because my computer is on right now.
it's
so I was
cool.
working on
It's cool. I'm making fun of you for a reason though, because at the end of the day, just get in the habit of locking these scripts middle mouse wheel, and then this lock button when you open up a script that you don't know anything about, because God only knows he might be solving some stuff that you don't care about. And we'll sit here during class and we'll wait 5 minutes for something we don't need to wait for, right? So let's see what happens. We probably should see a robot instance of robot open up. Should we see an instance of robot open up?
Yeah. It's
So
opening.
you tell us how this works. We'll do
It's
a
open already, right? The robot.
The computer just did that.
Excel is opening too.
Let's see if anything pushes over. Probably not, right? Because we just turned that thing to
Yeah.
false.
Yeah.
All right. I think the last time we were all together, we had a very simple version of this script, right? And this time we have a little bit more complex of a version. I think let's just show how it works, right? So I turn this on. We should see some panels popping up in here.
But no constraint at the moment.
Can't do the constraints. We can't.
Because the way we did on Monday
Mhm.
was getting nods from without the constraint, like just getting nods and then having the constraint on different way.
So
So it was not automatic. You had to like open it and then go back to Grasshopper.
you had to mesh it basically.
Yeah, mash. You have to mash it and then go.
Let's do that. We can do that, right?
Yeah.
Okay. So our methodology was a little bit manual. Nothing wrong with that. Keeps you in control, especially for things like meshing. You don't want it to be completely automated until you really know what you're doing, right? I think we said we wanted Delaunay and Kang. I think this was like 0.1. We wanted it to be fine. And that, in general, I think was our settings. This is a robot thing. This comes with years of experience and understanding what makes a good mesh for you. And obviously, it's an engineering decision in terms of, is that the mesh that we want or not? Okay? For now, I think we're able to,
Get the nodes.
I'm going to pull in all those nodes we just created. So we created all these things back here, right? Let's pull them into Grasshopper.
Takes a while. I don't know why this whole process takes quite a while.
Yep, looking down. So, ooh, that one came up in the wrong place.
Oh, where is that? Why is that coming?
So, did we, I forget, was it, I don't think we had that many people here. Monday we did our thing.
Yeah.
So we had said that the only way for us to get this thing to work properly is, instead of actually sitting here and putting around an pinned edge restraint, if we put in a pinned edge restraint, actually what we were witnessing was we were developing tension on this side and compression on this side. So on Monday we discussed, hey listen, if we look at our stress plots, we're getting hogging and sagging moments. And from what we described is a spider connection that's supposed to represent looks maybe something like this in reality, where it actually physically will act more like a pin at that spider connection. So we should not be able to witness tension on a hogging moment. We want to see this entire panel going straight up, sagging moment in one direction, right? So that would be an incorrect way of modeling it using the edge supports like we were doing. Everybody okay with that? Engineering-wise, that's incorrect. So what we said is what's the way that we can get that behavior, but computationally? Said what would be great is if we had a node here that was actually pinned, analytically constrained to be a pin, and then off of that we had a bunch of constraints, rigid links, right? Would everybody agree that would probably get us the right type of behavior, right? That's a question.
Yes.
That's what we want. Do we want it to be a pinned connection basically at that point at the middle of the spider. Eugene, is that cool? Is that okay? Okay, fine. Because that's.
But that will be the same for computers.
No.
No, it won't.
The
No, it won't.
analyze like calculating wasn't.
So if you think about it, if this guy has actual width, right, and you give him a pin here and a pin here, imagine if it was a continuous beam, right, going across this and this, right? Is this thing a pin overall? No, because this guy can actually do things where now he has the ability to give us a push and pull, if you know what I mean. So there can be a sort of differential. This guy can be pushing down and this guy can pulling up depending on what you do. Because you've given him a base of width B, he has the ability to give you a push-pull. And our connection is not able to give us a push-pull, from what I understand. Right, so if we want to see this panel pivoting about this point right here, which would be on this image, this point right here, we have to give it analytically one pin and nothing else. Make it such that it does do that. Either way, as you say, it's very close. And what we noticed was, we said, that would be probably another way of doing it, but it's, oh my God, could you imagine having to do this every time? Click, 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 apply rigid link, master nodes, slave nodes. So what did we do? Let's see if it worked, first of all. Yikes.
Why is it going into 1 point?
Let's figure it out, right? So what we're noticing here is first of all,
Got all the nodes, for sure.
let's pull in the nodes. Okay, so we've pulled in those nodes, as you can see here in Rhino. We've pulled them over from robot into this space here. Let's zoom in on one of them. So our goal is, if I just quickly show this one. So we pulled all of them in, right? Then Sung did some fancy math and stuff like that, and he got down to just the ones that we wanted, right? What's that called when we do that? What's extremely important skill, right? Because that basically taught the computer. This is when we did the smiley faces. This is chapter 2, right? We've said, please take all of this data and use something to actually be able to select some of the data. So we have all of this data, and we're going to select some of it, some part of it, right? So in this case, Sung has said, I have all of this data here, and I want to get down to just part of it. How's he done that? Inside of here, he's enabled us to actually, he knows where those points are that he cares about. So where did these come from? Did these come from robot? No. If we chase it upstream, he already knows. We called it faceted, but really it's coming from up here. Back when he had, back in the very beginning of the script, he said, I'm going to make 4 faceted spider circles. So he already knows in space where in Rhino there should be new nodes. Remember, Rhino created these points in space, these nodes. Remember, this is the important thing. The difference between a node and a point. These are just points in space. At this point, no pun intended in the structure, we have curves actually. That's why we see only curves. If we go and look at what he does here, he takes in those curves and things called nodes, which you can't really see if I click on them, right? You see I'm having to do this thing called geometry to see a preview of them, because there's a huge difference between these two objects. What is a node? A node is all this jazz right here, a position, an orientation, a support, blah, blah, blah. What is this guy? He's a curve. Be more specific in here. The curve has endpoints, and what he's done is actually got the points, right? So you're telling me the nodes, they have geometry, and that geometry should line up pretty well with the original stuff that we used to create them. So if you see here, lots of information, some information. Lots of information, some information. To our eyes, it's very easy for us to come in here as humans and say, well, basically, the ones we care about are definitely not these guys, start whacking these guys out of the picture. But the computer doesn't know that. So what we do is we search. We say, from these points, we do a closest point search, which means that from each one of these points, we look out of these points for the closest point. And what comes out the back is an index from this cloud of the points which associate to these guys. I'll say that again. We're getting an index from this list. So 556 points here, nodes, let's say, but we've converted them to points now. 556 points. Where in that list, so index 60, index 138, index 51. So if I just do a list item over here again, and I say, please pick these items out of this list. Looks like I've done it, right? So you sit there and you scratch your head and you say, well, why did you have to create this again? Why doesn't this guy show anything when I click on him, right? And it's because, again, this famous structure of filtration, the famous filtration structure is data, down is some metrics, some data, other data that you create, and then you basically, this is sacrificial. Sacrificial. We're just using that to be able to get us back to some sort of logic gate on the original data right here to be able to select the original data. So what has Sung done? He said, take this data, make some data with it. So he's actually combined that data. He's first of all created data with the original data. He's created these points in space. These are actually points. These are nodes. You see how it says BHoM, structures, elements, nodes? That is not the same as what comes out here, which is points, which is why when I click on him, we see something. When I click on him, we don't see anything, because it contains more information than just geometry. But he's also mixed in, so this entire thing down here is what I'm calling in this sketch the metric, right? He's using all of that jazz right there just to get down to one thing, this number, which is basically telling him in this list of 556 objects, here are the 104 objects that you care about. They're at indices this, and this, right? I'll just draw it just to make sure we understand. The computer, this is a great one. The computer does not see this. You see this. The computer, when he sees that, what does he see?
Numbers.
He does not see that. That's you. The computer just sees this. Item, 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 item. And in this case, he seems like he sees 556 items. You see 556 items too, but he sees them in terms of they're just here. I don't know what they actually mean. So it's your job, and what Sung has done here is he said, I also have these items. So what I want to know is that items, again, those ones look like this. Boom, 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 right? So these are the spider connections. I missed my whack. And these are just all the mesh nodes. So these are from Robot. Right? So now we need to find out, hey, you might think, oh, it's just this guy goes to this guy goes. That's not the way it is, right? The computer says these are just two lists of information completely separate from each other. And what Sung has done is said, hey, listen, find from this guy the closest point to me, and then eventually related that back to, that means I'm with him. That means I'm with him, right? That means I'm with him. Okay? Again, I've taken this guy, I've converted him to some other information. I've actually mixed in some other jazz here just to get down to the ability to say, actually, those numbers right there are the money for me. Modify the original data set based on this information. And what happens? Not so visual here. You go down to 104 objects. So just looking at the numbers helps you, right? I went from 556 objects to 104 objects. And what does that look like physically? It looks like I've gone from this to this. Okay, again, I'm using this to be able to see it visually. This guy says, I'm a node, now I'm not. I'm a point. I can see points. So before this thing, I saw this picture. After this thing, I see this picture. Very useful in terms of being able to see if you've actually got the information correct. Okay, so now what Sung has done is he said we've done this before in previous classes where we take a bunch of points and we average them, and there's your problem, Sung. Somehow, some way.
How's the average there? Oh, because it's
all four.
we gotta graph it.
You lost your graph somewhere in here. So your graph should be based on spiders,
Yeah.
right? So you lost your graph here.
Okay.
So does everybody get what's going on here? What we expect to see at this point, we saw it on Monday, was instead of seeing one point out here in space,
That's the average. Yes.
that's the average of all the points. We want
Yes.
a point here and a point here, not a point here.
Yep.
So what we really wanted, based on that original sketch that I showed, was we want the master node. We want a node right here that will be the master node, and then we'll draw a bunch of rigid links off of him, be the slave node. Right? But Sung originally, right now, he's just said, here's 104 points. Please average them. So is there anybody against what's happened here? From a logic standpoint, logically, you're getting the right answer.
Yeah, it is.
From an engineering perspective, are you getting the right answer?
No, we're not.
No, that's a bad business there, right? So what we want to do is we want to make sure these nodes are separated into 4 different groups, right? Sung has somewhere down here, if we just chase this back, eventually we'll find a flatten. And lo and behold,
Because
there's your flatten.
flattened it there.
Can I undo
Yeah,
that?
yeah, you can.
Oh.
Fine.
I'm going to lock it because I think we have a dead man switch here, which is not going to be good for us.
Yeah.
Because if I left him on, right, he
yeah,
would push it again.
Push it again.
Okay, got to be careful with these dead man switches, guys.
Then
Okay, now let's see what happens. It is interesting that it takes this long. We're going to have to get into that.
I really don't know why. And especially on this particular script, it takes at least like 30 seconds.
It's very strange.
Up to like 1 minute.
Because all we're doing in that part of the script is pulling some stuff, which, okay, that takes 5 seconds. He's telling us that.
Yeah.
But this is obviously taking a lot longer than 5 seconds.
Much longer. It takes like a minute to actually calculate everything.
We'll figure that out.
That like the rigid and everything.
So everybody understands, right? We're trying to grab these guys, right? Which are related to, they know where they are in robot. So for instance, he's grabbed those guys. Let me just show you something real quick. If I explode, and I explode the custom data, there's a robot ID associated to those guys. So that he knows, in robot, I'm called this. So we're one step away. You guys know how to assign a rigid link in a finite element software, right? You come in here and you go, I think it's under additional attributes, rigid link, and then the master node has a number, right? And then there's all these child nodes and blah, blah, blah. They all have numbers. It's all number-based, right? I don't want to spend my life coming in here all day and precisely having to click this thing, right? It's really dumb. So we've finally gotten down to that position. It takes 30 seconds just to push it over. But I think that's because we're doing it in an efficient fashion. So we'll talk about that. So effectively, has Sung done what he wanted? We can see it actually on the screen right now. He's created that point in the middle. So that's a point that is not in the model right now. How do we know that? Based on what I just told you. So he's created that guy. If I take him and do the exact same thing, again, these are all nodes. So if I copy this guy and explode these guys don't know who they are. They don't have an identity in robot. So in other words, they need to go over there, right? How do we make information go from one software to another? It's this one, right? Push. Now in this case, let's not get too bogged down in why this isn't working so well. I think we could flatten this here. I don't know why we're not flattening this here because if we flatten it, we lose our data tree on the backside.
Yeah.
So we can quibble all day long about what the right thing to do here is, but we've been lazy and we've said we'll push it, we'll maintain the data tree, and then on the back side of things here, I'll have a data tree of 0, 1, 2, 3, 4. Again, what are those? 0, 1, 2, 3 are the spiders. Then I'll have the slave nodes, which are 0, 1, 2, 3, but they're having 26 items in each one of them, right? What is that? So this master node is the guy on the screen right now, and then the 26 is the slave nodes. And then what do? We push it. So actually, we should already see the picture looking somewhat right in here.
No, you didn't, because you locked it.
Yeah, so what we're going to do is we're going to start over again. Nice and slow, and show everybody how we did this. Okay, step number one. I'm going to turn, first of all, we're big boys and girls now. Button. We're going to button this script up so that it's no longer dangerous to just kind of, we don't ever really want to see a script where you click a button and everything goes.
Yeah.
For finite element analysis, that is just dangerous. You don't get anything. Now this one needs to be a toggle. This one does need to be a toggle.
But that one is the one that getting all the nods. But
We'll do it. It does need to be a
okay.
toggle, but we're just going to do one thing at a time here. Finite element analysis should not be fully automated, period. It should be scrutinized. And even us, all of us sitting around the table on Monday and in the past few weeks looking at this, we missed because we're focusing on this because it's important to focus on this now for your computational education. But we missed that, hey, listen, the results we're getting out were bollocks. And we changed that. Now we're not getting that. But that cannot be forgotten in finite element analysis, that effectively it's your responsibility to make sure that the results line up to scrutiny. And with computation, if you're not doing that, you're going to get into a world of trouble very quickly. Okay, so there's our friend Mr. Panel. We said that we were going to use a certain type of mesh, right? So let's just put that on. We could do this computationally, but again, I think it's worth, for you guys, I know you guys are new to robot, fine-tuning this yourself. It kind of reinforces the fact that you should be people who are doing convergence analyses and stuff like that. We're not playing, this isn't just a Candy Crush Saga, right? This is a very expensive piece of software that if you screw it up, it has real ramifications. So you should know that when you look at that, that's a crappy mesh. And as an engineer, go in there and say, why is it a crappy mesh? And figure it out. Probably.
element size.
That's better. I can accept that. This ain't a lesson on robot, all right? So now we say, okay, it's gone over, turn him off. Let's pool over the nodes. Okay, and this takes a few seconds. So all these nodes that we've just created, they're going over to Grasshopper right now. Again, they all kind of are self-aware in the sense that they have robot IDs now. Sung has grabbed what looks to be the right guys. And then he has created, hopefully, yes, he's created some points in space that are going to be our supports. And now if we press this button, we should see those points show up in the middle here. This is the one that takes 30 seconds for some reason. I know why, but it's not really important for this particular lesson.
Why?
You're putting it, these components are really set up to be run as a list going into them. So it's probably computationally most efficient. We see it, you got it over here.
Yeah.
But he's looping, so he's running a
It's like-
whole entire script. And behind the scenes, it's actually more efficient to feed him everything, and then he'll do everything at once. So you're getting a lot of baggage because of the way we're doing it. Having said that, we decided that it would be most quick. We get the quickest wins by doing it this way. Having said that again, I think we might be in trouble, because if you use the button, I don't think this guy propagates forward. Oh, he does. Nope, he's empty, right?
Why is it empty?
Because we turned him on and then off, right? So he deleted everything,
I deleted everything.
right? So he's empty. So
So it has to be just Boolean true.
yeah, so we have to do the toggle there. Again, we'll fix this in due course. But the key here is that we're just trying to get a quick win. 30 seconds in the grand scheme of things is way better than what you could do by hand anyways. We'll work on fixing this after we show this to everybody. We actually probably can get to that today. All right, so 30 seconds here. Any questions in this 30 seconds?
I do. I need to make a Maulian entrance now, and I actually don't. I tried to find elements that how to make it BHoM object, but kind of failed. So.
All right, we'll deal with that. So we just pushed over our guys here, and then let's watch the Shazam moment here. So Shazam happens when we,
Click on that.
when we just watch these rigid links, which would have taken 30 seconds a piece to put up there. Boom.
That takes a while.
Yeah, it should be instantaneous, but we should see. There we go.
It runs 1, 1, 1, 1, 1. I don't know why. It runs like 1 by 1.
Yeah. Oh, yeah, it's very strange. Well, it doesn't matter. We got it done way faster than any of us in this room could have done manually. I don't care who you are in this room. You couldn't have done it faster. And now if we run it, right, first thing an engineer does, he goes and he says, hey, listen, let's see that deflected shape, let's say. So let's see it. Ooh, Lord have mercy. That's a good deflected shape. I'm not even a facade engineer. Right? That's a perfect one-way spanning slab.
The reason why we did this, because when we were doing this, the before, it was going this, and then it was like flat.
So if you can imagine before, we were actually getting that this slab here had the tendency,
doing that.
it could do this, because you did have the ability for the guy to push up on you here, and you had the ability for the guy to push down on you here. So that
No,
push-pull...
it was actually kind of flat there.
Well, exactly. I haven't drawn it completely correct, right? But effectively, this guy was acting as a push-pull, because you had a pin.
We're only going like in between that openings.
So if this thing's meant to be act as a pin, you can't have pins all the way along this area here, because that together acts as a fixed support that can actually take compression and tension. Now we're seeing behavior that looks very good. If we go to results and we go to maps, I'm going to align my stresses to...
I'm not sure you have a load though.
Oh, I do. Dead load. Dead load's on my side. So direction is in terms of the global X. My layers, I'm going to change my layers to middle. And I'm going to change my stresses to XX in the X direction so I understand how it works applied. Why don't I see anything here for the XX direction? So the XX direction is aligned with the global X. And XX is, so then this is stress in this direction. Why don't I see anything? For the middle layer, stress XX. Again, keeping in mind that XX is kind of what we're playing with here is just the sigma 1, right, sigma 2 type of, sigma 1, 2 type of thing. We shouldn't see any in-plane stress for this guy, especially on the middle layer. No way, right? The middle layer, this thing isn't in compression. The middle layer, if this thing's in bending, certainly the middle layer is where the neutral axis is, right? So if we change that parameter to be lower or upper, now we should see some stuff. If we do absolute maximum, we should see pretty much the same plot, just different colors, right? And especially if we change it now to the YY direction, that's where we definitely should see our nice, beautiful sagging moment. And that's where we saw it last time, is we saw big hogging moments over here. And that was a red alert. Okay? So that's the way you can use the BHoM to create a quick finite element model. We went over it the first time, and Sung now has mastered this and how to programmatically add supports to edges and whatnot, right? Kind of. At least we are in the space of being able to create reasonably quick, very good quality finite element models without wasting our time clicking on spider connections and stuff like that. All right. So other than Sung's question, we have any other questions? One thing? You're the most familiar with this other than Sung. Any questions?
So now we have done the one panel. So now we gotta, as you were quote unquote money making, we need to make this blow up and make actual curtain walls.
Now, let me ask a question. So, the curtain walls themselves,
Uh-huh.
if this is one panel on a curtain wall with 50 panels on it, right?
Mhm.
Certainly the design of the panels, if they're all the same, is this model right here.
Doesn't matter. I don't know.
I'm asking the group. So if we were to design the panel, the glass, would this be the model that designs the thickness of the glass effectively? From a ULS perspective, how would we do that normally? Before we start trying to make a big model with 50 million panels in it, it's important to know the reason for it. The reason for this model, if it were me looking at it, is we must want to know what the deflection of this panel is on his own and what the thickness is under a ULS condition. Is that right, Jane? This would be how we size the glass for panel type A. What you're describing is more panels. So if we have multiple panels, right, we would have to do multiple designs, right?
But I would say that will be a detailed design.
Yeah, I think this is good enough, but I'm wondering the support, is it like three directions?
It restrains only translation X, Y, and Z. No rotation.
This is also transfer the moment.
It does not.
No, it does not. But at the full point, usually we only restrain the three directions in one point, and other point we release like
The lateral. So that it doesn't have the ability to do like catenary reaction or something. That's very good. Like so.
Yeah.
and the lateral will only be on like at the top. This will be like either two. We keep it that.
So only two up there too
Yeah,
will be
yeah.
just like actually pinned.
Yeah.
The other
So
two should
Will
be
be like
more
releasing
flexible.
I completely agree with that too, because obviously we're doing this quickly. If we want to make sure the boundary conditions in a finite element model, just so you know, are the biggest dangerous, because you're actually throwing in there something that's infinitely rigid, and nothing in the world is infinite, right?
Yeah.
So I think what you're saying here, Jane, is that we'd probably put one quote unquote pinned connection here, right? Probably another one here, right, so that it's stable, right? You need at least two so it doesn't want to rotate around the world. Or you would just do,
That will release the lateral. One of it will be.
yeah, so what if we just did, I mean, you could just change this very easily actually, but all of them get, in this case, if it's up and down, right, they would all be getting at least that, right?
Yeah.
And then one of them needs to get this direction, or else it slides left and right, and another, and it needs to get also this direction. But then it's not stable rotation-wise, so it probably needs this as well. So he can't move this way, he can't move this way, and he can't rotate this way.
Yeah.
So he's stable. So boundary conditions, we've over constrained this problem. So we could actually develop axial loads here where we can't. In reality, you're saying the glass cannot actually go into axial load, let's say. Okay, we can change that. Obviously, that's a very easy thing to change, and it's applied literally. Instead of this, you change that, right? And potentially you have to create 4 of them. And the good news is because this script is what you'd use to create a 4-spider panel, once you set this up once, from now on, every time you run a finite element model on a piece of glass, the engineering quality, because we've all decided all this together over the course of a few weeks, is beautiful. There's no problems whatsoever. We're not having the next graduate who comes in, he's going to make these mistakes, for sure. But it will not happen on our projects because we're like, well, we already have a tool for that, and we've designed it together to have good engineering quality, plus it's fast for commercial abilities, okay?
But will it be able to like adjust the support point so it can optimize the
We can start that next. Like, if that's what you guys want to start working on, we can start doing that. I recently, do I have a video of it? I do. I recently did something like that. That's a bigger thing. So I would say we kind of try and avoid it for now. So I recently had something that was kind of like this, where I was just all night, I was just sending over robot models into Robot. They would obviously change in Rhino, right? And then they'd show up in Robot, right? They'd run, I'd extract the results, right? And you could use this to optimize, as you say, the best location. I think for now, there's very few times in my career where I've seen that you can do that effectively, better than your brain. So I actually have more faith in your brain and the tool than doing it this way, right? I think this is extremely cool, and all engineers tend to want to do this, but it's actually never beats your brain, unfortunately. So having said that, let's keep that in our heads, because one day we could find that actually for facade engineers, it's way more. For this problem, I highly doubt you guys can't do this in 2 or 3 iterations and get it optimized. So, but when the problem gets more complicated, then maybe we're talking about that.
And can I add one more point at the middle?
Yeah.
Adjusting the numbers in scripts.
Oh, like there.
For example, now I want 6 points rather than.
Oh, like having here and here. Yeah. That's easy.
So that's one of the, I guess, if we just wanted to make a generic tool that everybody can use, that would be one of the things, right? I would say probably making this tool generic and able to be just a standard tool. Again, we all have to understand what's going on in here.
Trying to make it simple as possible.
Yeah.
But it's
Well,
it's
we're
kind
not
of
we're not there yet, too. So there's the loading aspect of things, but just to get the model set up, right, is this stuff right here.
there, kind of in a way.
I personally, I think what this should be the input to this, because you've done everything right now as kind of parametric. So you've kind of tried to make it such that it's a Grasshopper script.
Possible people to actually use it.
Yeah, but I think, but in your quest to try and make this, everybody likes as architects, they love, oh, hey, it's sliders, and we'll sit here right now, and ooh, oh, that's
No.
not so.
No.
That's not so fun, right?
That's not a good idea.
Oh, we have it turned off, don't we? Oh, it's triggering the other one. Toggles. Toggles are the devil.
There we go.
Let's just turn these guys off, right? Again, everybody loves the idea of, hey, give me a slider and then we'll do wonk, wonk, wonk. Come on now. That's not how we work normally. Every situation's unique. So if literally it's always that we can boil it down to geometrically, are you telling me that geometrically 99% of the times, if you tell me 99% of the times you would be happy with something that does wonk, wonk, wonk. In other words, this, right, this, it looks cool, don't get me wrong, right? If we're just missing the ability for you to add in on this, a parameter that says, how many go here, how many go here as well, then I'm happy to say we add that, we're done. But my guess is actually, eventually, it'd just probably be quicker for you guys just to be able to go sketch, 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 boom, 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 and done. I don't know. So don't, I'm not saying what to do. Just kind of remember, it doesn't need to be, because this is all modular, you don't need this to be a 100% tool that you open up every time and it works for you. You can actually be smart enough to say, I have a bucket here that takes in spider curves. I have a bucket here that takes in a panel. That means that literally I could do this problem again very easily right now just by doing this. Yep. Boom, boom, and boom.
That will not work.
Why not?
Just because that's out of 4 sides, not 5 sides.
So that's where I think if we want to make things generic, that's what we talked about yesterday.
Yes.
To make this thing into something that isn't inside of here, very much geared towards.
Probably that one, yeah. I will not run.
Yeah, we have to fix it.
Yeah.
That's a data tree structure thing.
Yeah, that's
But certainly, we're getting closer to the ability to saving a ton of time.
We don't have octagon windows, right? Like it's mostly triangular or rectangular. No.
What if we did like a really cool like dome project? Wouldn't we have a higher chance of having something that wasn't like triangular, for instance? It could be triangular.
Yeah, triangular is more common.
Yeah, more because
I mean,
they cut it down because we cannot make the huge glasses. And the end up we always like cutting it down square or up to the triangle.
Right, so this, I
So
guess,
that's why I was thinking.
me going more is probably stupid, but going less is definitely on the table.
Yeah, so like I think having one that runs a rectangle, one that runs triangle.
Or just one that just works with a
Work
curve,
everything.
and it just does it, like, I mean,
Okay,
that's the
that
thing
works.
is, we can do that too.
Yes.
Like I said, in my mind, my tools, the way I do them is just, I wanna just be able to come out here and sketch, right? I mean, it's not actually, to me, that valuable, to not be able to just quickly do that. Because most of the time, actually, the shape of that thing is dependent on other things, like the drawings from the architect or something, which the computer can't
Yeah.
read. So your brain is very useful. Don't knock it. Like, we need that stuff going on. So, in terms of where we go next with this, so that's basically the final script in terms of a very basic functionality. Here's how you make a glass panels finite element analysis tool, right? Where would we go next with this? Being able to set up, because I honestly think if you just have 5 different panel types and you want to set up the models, we're done. If that's how we design glass panels with that finite element.
This is what the only one's messed up. I don't know what because I really don't have much of experience on this in this field, but what Pyongyang want is be able to change mullions and transom within the width and height, both sides, and then make.
Welcome to my
never
life.
works.
Welcome to my life.
This doesn't work either. You can see it. So like he want